Hi, I'm Rudraksh and I'm going to talk about the design of the CPU and how this can be translated to a HDL code. This diagram is the proposed design for the CPU architecture in which I am going to use the implement and explain the HDL code of the CPU. In the following diagram, the CPU consists of several logic gates such as the ALU, A register, D register, PC and the multiplexer. Since we have built most of these logic gates from the previous task in this until it will be easier to implement the CPU HDL code with them. The first step to implement the code is to derive the API of the CPU. The API specifies the chip name, the input and the output pins, and the function of the CPU and an additional comment. So we will start off with an abstraction of this chip by hiding all the logic gates in the diagram so that we can easily identify the input and output pins of the CPU. Now we can clearly see the input and outputs of the CPU as shown in this diagram. There are three inputs coming into the CPU from different sources in the computer: the instruction memory and the data memory. These inputs are the instruction in M, and the reset, the instruction input, is from the instruction memory or the row which is value of the selected instruction memory register. This instruction can either be an instruction or a C instruction. On the other hand, in M is the value of the currently selected data memory, the value that the CPU uses to perform its operation. Here we can clearly see a diagram that further shows that the CPU is connected to the instruction memory and the data memory. This diagram was used to implement the hack computer in one of the tasks that I have done previously. Here we can really see that the CPU takes its instruction input from the instruction memory and also take the value of the selected data memory. As one of its input, the register input is a value that tells whether we bring the CPU back to its initial state or to be specific to the start of the operation of the CPU. All over again, furthermore, along with the input, CPU has several outputs that are connected to the instruction memory and the data memory as well as. These inputs are called as write M at M address, M and PC or the program counter. In the given CPU architecture, we can see that the ALU gives an output that is written to the data memory. In order to do so, the ALU must specify a few things. First, the content that the CPU is going to write into the data memory, which is stored in the outm. Second, the address of the write operation in the data memory. Basically, this is where we want to put the content in the data memory. Lastly, the output that allows CPU to write the content to the data memory. The program counter holds the address of the next instruction, which will then be fetched, decoded, and executed by the CPU in the next cycle. Now that we have identified the inputs and outputs of the CPU architecture, we can now implement the code of the CPU. This is the HDL code of the CPU that was provided in the task resources. It consists of the chip name and the name of its input and output pins. Since we are implementing the CPU chip, the chip name that we are going to write for this code is CPU, as shown in the code. The input pins of the CPU will consist of 16-bit in M 16-bit instruction and reset on the other hand. The upper pins of the CPU will consist of 16-bit outm, writem, and 15-bit address. 15-bit PC, the input and output in the header section of the CPU do correspond to the design. The first part of the parts select section in the CPU HDL code We have three different gates: NOT gate, AND gate, and mux16k. These gates allows the CPU to function and perform specific operations. Firstly, there are two types of instruction coming into the CPU from the instruction memory. These instructions are the A instruction and the C instruction. A instruction has a symbolic syntax of add value. This value can either be a number, that is a decimal, non-negative number, or a symbol. If the value of an instruction is a number, then the instruction will set the contents of the A register to the specified value in the instruction. If the value of A instruction is a symbol, then the instruction will set the contents of the A register to the value that the symbol points to, and this value will not be the actual value in that memory register. On the other hand, C instruction has a symbolic syntax of test equal to comp and jump. This instruction performs a computation on the CPU which is stored into a destination register or a memory location. It can also tell us the CPU to jump to another instruction memory address that is pointed by the value or the symbol. We can see that the NOT gate is used to tell whether an instruction coming into the CPU from the instruction memory is an instruction, but the first CPU decodes the 16-bit instruction into an opcode and 15-bit value. If the opcode is 0, the instruction is an A instruction, whereas if the opcode is 1, the instruction is C instruction for the instance. If the instruction coming into the CPU from the instruction memory is an instruction, the CPU takes the specified 15-bit value and stores the value into the A register that was taken from the CPU architecture. The A register can be fed by either the instruction input or the ALU output. If it is a C instruction, it performs the computation in the ALU and the ALU output is fed to A register. We can use the AND gate to determine the instruction of C instruction. A 16-bit multiplexer is also used to select whether the instruction or the ALU output is stored into the register. In the next part of the code, we have an OR gate. The load bit in the register would be 1. If either the A or the ALU output is fed to A, on the other hand, the A register is used to store the value that is fed into the A register. It takes in the output and the register from the multiplexer and the output load A from the OR gate as its inputs. The output A out then generates the content or the value that is currently stored inside the register. Next is another mux16 which takes in the output of the A register and the value that is currently selected in the data memory register in M. This will select which one to output, or M, either A or M will fed to the will be fed into the ALU depending on the 12-bit instruction value. The AND gate is employed to determine whether the ALU output is loaded to the D register. The D register is then implemented to load and store the value of the D register from the ALU. Next up is the ALU gate. That the ALU computes a function on two inputs, which in this case would be the value that is stored in the D register and the value of either the A or M registers, and then generates output. It consists of input control bits such as the ZX and XZY, NY, FNO, which are indicators of the function is computed on the two inputs to produce output. Whereas the output control bit such as the ZR and G determine the properties of the result. The following code, which consists of 2 or 16s and an AND gate, sets the ALU outputs in order to successfully write on the data memory. The first or 16 code line determines the address of write operations. The second one determines the content of the data memory, and lastly an AND gate that outputs the value that allows CPU to write the content to the data memory. The program counter, or also known as PC, is a register which contains the address of the instruction to be fetched next. In this part of the CPU HDL code, the load bit of the PC is determined by the jump bits and the ALU outputs. Basically, these lines of code determines jump conditions and check the ALU output to see if the conditions are met. If the instruction is C instruction and the condition are met, the program counter is loaded with the value that will ask the CPU to jump to the specified value or symbol. If the PC is not loaded, then PC is incremented. Incrementing means that the CPU will read the next instruction, and so this is how I understand and will implement the HDL code for the hacked CPU. Thank you for listening.